Hello everyone, welcome to the second part of Semiconductor chapter 14 class 12th and I am starting here from 14.5 PN junction. इसके पहले की जो ऑडियो बुक है उसका डिस्क्रिप्शन में मैंने लिंक दे दिया है, तो आप उस पार्ट को वहाँ पे सुन सकते हैं. तो बच्चों उसको ज़्यादा से ज़्यादा शेयर करिए, अपना ज़्यादा से ज़्यादा प्यार करिए और अगर लगता है आपको ये वीडियोज़ आपकी हेल्प कर रहे हैं, ये ऑडियो बुक्स आपकी हेल्प कर रही हैं, तो आप इसे लाइक ज़रूर करिएगा. सो चलिए टाइम वेस्ट नहीं करते हैं और स्टार्ट करते हैं. 14.5 PN junction. A PN junction is the basic building block of many semiconductor devices like diodes, transistors, etc. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. We will now try to understand how a junction is formed and how the junction behaves under the influence of external applied voltage, also called bias. 14.5.1 PN junction formation. Consider a thin p-type silicon semiconductor wafer by adding precisely a small quantity of pentavalent impurity. Part of the PSI wafer can be converted into NSI. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and a metallurgical junction between P and N region. Two important processes occur during the formation of PN junction: diffusion and drift. We know that in an N-type semiconductor, the concentration of electrons is more compared to the concentration of holes. Similarly, in a P-type semiconductor, the concentration of holes is more than concentration of electrons. During the formation of PN junction and due to the concentration gradient across P and N sides, holes diffuse from P side to N side and electrons diffuse from N side to P side. This motion of charge gives rise to diffusion current across the junction. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor positive charge is immobile as it is bonded to the surrounding atoms. As the electrons continue to diffuse from N to P, a layer of positive charge on N side of the junction is developed. Similarly, when a hole diffuses from P to N due to the concentration gradient, it leaves behind an ionized acceptor negative charge, which is immobile. As the holes continue to diffuse, a layer of negative charge or negative space charge region on the P side of the junction is developed. This space charge region on either side of the junction together is known as depletion region, as the electrons and holes taking part in the initial movement across the junction depleted the region of its free charge. Figure 14.10. Here you can see the diagram. The thickness of depletion region is of the order of 1/10 of micrometer. Due to the positive space charge region on N side of the junction and negative space charge region on P side of the junction, an electric field directed from positive charge towards negative charge develops. Due to this field, an electron on P side of the junction moves to N side and a hole on N side of the junction moves to P side. The motion of charge carrier due to the electric field is called drift. Thus, a drift current which is opposite in direction to the diffusion current starts. Again, figure 14.10. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extend, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals the drift current. Thus, a PN junction is formed. In a PN junction under equilibrium, there is no net current. The loss of electrons from the N region and the gain of electron by the P region causes a difference of potential across the junction of the two regions. The polarity of this potential is such to oppose further flow of carriers so that a condition of equilibrium exists. Figure 14.11 shows the PN junction at equilibrium and the potential across the junction. The N material has lost electron and P material has acquired electrons. The N material is thus positive relative to the P material. Since the potential tend to prevent the movement of electron from the N region into the P region, it is often called a barrier potential. 14.6 Semiconductor diode. A semiconductor diode, figure 14.12, is basically a PN junction with metallic contact provided at the ends for the application of an external voltage. It is a two-terminal device. A PN junction diode is symbolically represented as shown in figure 14.12b, this diagram. The direction of arrow indicates the conventional direction of current when the diode is under forward bias. The equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of PN junction diode under equilibrium without bias is shown in figure 14.11a and b. It was the previous figure. 14.6.1 PN junction diode under forward bias. When an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal 14.13a, it is said to be forward biased. The applied voltage mostly drops across the depletion region and the voltage drop across the P side and N side of the junction is negligible. This is because the resistance of depletion region, a region where there are no charges, is very high compared to the resistance of N side and P side. The direction of applied voltage V is opposite to the built-in potential V0. As a result, the depletion layer width decreases and the barrier height is reduced, that is 14.13b. The effective barrier height under forward bias is V0 minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value and only a small number of carriers in the material. Those that happen to be in the uppermost energy levels will possess enough energy to cross the junction. So the current will be small. If we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have the required energy. Thus the current increases. Due to the applied voltage, electrons from N side cross the depletion region and reach P side where they are minority carriers. Similarly, holes from P side across the junction and reach the N side where they are minority carries. This process under forward bias is known as minority carrier injection. At the junction boundary on each side, the minority carrier concentration increases significantly compared to the locations far from the junction. Due to this concentration gradient, the injected electrons on P side diffuse from the junction edge of P side to the other end of P side. Likewise, the injected holes of N side diffuses from the junction edge of N side to the other end of N side. This motion of charged carriers on either side gives rise to current. The total diode forward current is sum of hole diffusion current and conventional current due to electron diffusion. The magnitude of this current is usually in mA, milliampere. And now 14.6.2 PN junction diode under reverse bias. When an external voltage is applied across the diode such that N side is positive and P side is negative, it is said to be reversed biased. The applied voltage mostly drops across the depletion region. The direction of applied voltage is same as the direction of barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in the electric field. The effective barrier height under reverse bias is V0 plus V. This suppresses the flow of electrons from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the diode under forward bias. The electric field direction of the junction is such that if electrons on P side or holes on N side in their random motions come close to the junction, they will be swept to its majority zone. This drift of carrier gives rise to current. The drift current is of the order of few μA. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also there under forward bias, but it is negligible when compared with current due to injected carriers, which is usually in milliampere. The diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to sweep the minority carriers from one side of the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage but is limited due to concentration of the minority carrier on either side of the junction. The current under reverse bias is essentially voltage independent up to a critical reverse bias voltage known as breakdown voltage. When V is equals to VBR, that is the breakdown voltage, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes large change in the current. If the reverse current is not limited by an external circuit below the rated value specified by the manufacturer, the PN junction will get destroyed. Once it exceeds the rated value, the diodes gets destroyed due to overheating. This can happen even for the diode under forward bias if the forward current exceeds the rated value. The circuit arrangement for studying the VI characteristics of a diode, that is the variation of current as a function of applied voltage, are shown in figure 14.16. A and B. The battery is connected to the diode through a potentiometer so that the applied voltage to the diode can be changed. For different values of voltages, the value of current is noted. A graph between V and I is obtained as in figure 14.16c. Note that in forward bias measurement, we use a milliammeter since the expected current is large, as explained in the earlier section. One correction is there, that was not milliampere, that was the milliammeter. While a micrometer is used in reverse bias to measure the current, you can see in figure 14.16 that in forward. You can see the diagram here. The current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases significantly, exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or cut-in voltage. That is approximately 0.2 volt for germanium diode and 0.7 volt approximately for silicon diode. For the diode in reverse bias, the current is very small and almost remains constant with change in bias. It is called reverse saturation current. However, for special cases at very high reverse bias, the current suddenly increases. This special action of the diode is discussed later in section 14.8. The general purpose diode are not used beyond the reverse saturation current region. The above discussion shows that the PN junction diode primarily allows the flow of current only in one direction. The forward bias resistance is low as compared to the reverse bias resistance. This property is used for rectification of AC voltages as discussed in the next section. For diodes, we define a quantity called dynamic resistance as the ratio of a small change in voltage delta V to a small change in current delta I. RD is equals to delta V upon delta I. 14.7 Application of junction diode as a rectifier. From the VI characteristic of a junction diode, we see that it allows current to pass only when it is forward biased. So if an alternating voltage is applied across a diode, the current flows only in that part of the cycle when the diode is forward biased. This property is usually to rectify alternating voltages, and the circuit used for this purpose is called rectifier. If an alternating voltage is applied across a diode in series with a load, a pulsating voltage will appear across the load only during the half cycles of the AC input, during which the diode is forward biased. Such rectifier circuit as shown in figure 14.18 is called a half wave rectifier. The secondary of transformer supplies the desired AC voltage across terminal A and B. When the voltage at A is positive, the diode is forward biased and it conducts. When A is negative, the diode is reverse biased and it does not conduct. The reverse saturation current of a diode is negligible and can be considered equal to 0 for practical purposes. The reverse breakdown voltage of the diode must be sufficiently higher than the peak AC voltage at the secondary of the transformer to protect the diode from reverse breakdown. Therefore, in the positive half cycle of the AC, there is a current through the load resistor RL and we get an output voltage as shown in figure 14.18. Whereas there is no current in the negative half cycle. In the next positive half cycle, again we get the output voltage. Thus the output voltage, though still varying, is restricted to only one direction and is said to be rectified. Since the rectified output of this circuit is only for half of the input AC wave, it is called as half wave rectifier. The circuit using two diodes shown in figure 14.19a gives output rectified voltage corresponding to the both positive as well as negative half of the AC cycle. Hence it is known as full wave rectifier. Here the P side of the two diodes are connected to the ends of the secondary of the transformer. The N side of the diodes are connected together and the output is taken between this common point of diodes and the midpoint of the secondary of the transformer. So for a full wave rectifier, the secondary of the transformer is provided with the center tapping, and so it is called center tap transformer. As can be seen in figure 14.19c, the voltage rectified by each diode is only half the total secondary voltage. Each diode rectifies only for half the cycle, but the two do so for alternate cycles. Thus, the output between their common terminals and the center tap of the transformer becomes a full wave rectifier output. Note that there is another circuit of full wave rectifier which does not need a center tap transformer but needs 4 diodes. Suppose the input voltage to A with respect to the center tap at any instant is positive. It is clear that at the instant voltage at B being out of phase will be negative as shown in figure 14.19b. So diode D1 gets forward biased and conducts, while D2 being reverse biased is not conducting. Hence, during the positive half cycle we get an output current and output voltage across the load resistors as shown in figure 14.19c. In the course of the AC cycle, when the voltage at A becomes negative with respect to center tap, the voltage at B would be positive. In this part of the cycle, diode D1 would not conduct, but diode D2 would, giving an output current and output voltage across RL. During the negative half cycle of the input AC, thus we get output voltage during both the positive as well as the negative half of the cycle. Obviously, this is a more efficient circuit for getting rectified voltage or current than the half wave rectifier. The rectified voltage is in the form of pulses of the shape of half sinusoids. Though it is unidirectional, it does not have a steady value. To get a steady DC output from the pulsating voltage, normally a capacitor is connected across the output terminals. One can also use an inductor in series with RL for the same purpose, since these additional circuits appear to filter out the AC ripple and give a pure DC voltage, so they are called filters. Now we shall discuss the role of capacitor in filtering. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified output. When there is a load, it gets discharged through the load and voltage across it begins to fall. In the next half cycle of rectified output, it again gets charged to the peak value, that is figure 14.20. The rate of fall of the voltage across the capacitor depends inversely upon the product of capacitance C and the effective resistance RL used in the circuit and is called the time constant. To make the time constant large, value of C should be large. So capacitor input filters use large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified voltage. This type of filter is most widely used in power supply. 14.8 Special Purpose PN Junction Diodes. In this section, we shall discuss some devices which are basically junction diodes but are developed for different applications. Number 1. Zener diode. It is a special purpose semiconductor diode named after its inventor C. Zener. It is designed to operate under reverse bias in the breakdown region and used as a voltage regulator. The symbol for Zener diode is shown in figure 14.21a. See this. Zener diode is fabricated by heavily doping with P and N side of the junction. Due to this, depletion region formed is very thin and the electric field of the junction is extremely high even for a small reverse bias voltage of about 5 volt. The IV characteristics of Zener diode is shown in figure 14.21b. It is seen that when the applied reverse bias voltage reaches the breakdown voltage Vz of the Zener diode, there is a large change in the current. Note that after the breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. In other words, Zener voltage remains constant even though current through the Zener diode varies over a wide range. This property of the Zener diode is used for regulating supply voltages so that they are constant. Let us understand how reverse current suddenly increases at the breakdown voltage. We know that reverse current is due to the flow of electrons from P to N and holes from N to P. As the reverse bias voltage is increased, the electric field at the junction becomes significant. When the reverse bias voltage V is equals to Vz, then the electric field strength is high enough to pull valence electrons from the host atoms on the p side, which are accelerated to n side. These electrons account for high current observed at the breakdown. The emission of electrons from the host atoms due to the high electric field is known as internal field emission or field ionization. The electric field required for the field ionization is of the order of 10 to the power 6 volt per meter. Zener diode as voltage regulator. We know that when the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates. To get a constant DC voltage from the DC unregulated output of a rectifier, we use a Zener diode. The circuit diagram of a voltage regulator using a Zener diode is shown in figure 14.22. The unregulated DC voltage filtered output of a rectifier is connected to the Zener diode through a series resistance Rs such that the Zener diode is reverse biased. If the input voltage increases, the current through Rs and Zener diode also increases. This increases the voltage drop across Rs without any change in the voltage across the Zener diode. This is because in the breakdown region, Zener voltage remains constant even though the current through Zener diode changes. Similarly, if the input voltage decreases, the current through Rs and Zener diode also decreases. The voltage drop across Rs decreases without any change in the voltage across the Zener diode. Thus, any increase or decrease in the input voltage results in increase or decrease of voltage drop across Rs without any change in voltage across the Zener diode. Thus, the Zener diode acts as a voltage regulator. We have to select the Zener diode according to the required output voltage and accordingly the series resistance Rs. Second one is the optoelectronic junction devices. We have seen so far how a semiconductor diode behaves under applied electrical inputs. In this section, we learn about semiconductor diodes in which carriers are generated by photons, that is a photo excitation. All these devices are called optoelectronic devices. We shall study the functioning of the following optoelectronic devices. Number 1. Photodiodes used for detecting optical signals, that is photodetectors. Number 2. Light emitting diodes, LED, which converts electrical energy into light. And number 3 is photovoltaic devices which convert optical radiation into electricity, that is solar cells. Number 1. Photodiode. A photodiode is again a special purpose p-n junction diode fabricated with a transparent window to allow light to fall on the diode. It is operated under reverse bias when the photodiode is illuminated with light with energy greater than the energy gap of the semiconductor. Then electron-hole pairs are generated due to the absorption of photons. The diode is fabricated such that the generation of each pairs takes place in or near the depletion region of the diode. Due to the electric field of the junction, electrons and holes are separated before they recombine. The direction of the electric field is such that electrons reach n side and holes reach p side. Electrons are collected on n side and holes are collected on p side, giving rise to an EMF. When an external load is connected, current flows. The magnitude of the photocurrent depends on the intensity of incident light, that is photocurrent is proportional to incident light intensity. It is easier to observe the change in current with the change in the light intensity if a reverse bias is applied. This photodiode can be used as a photodetector to detect optical signals. The circuit diagram used for the measurement of IV characteristics of a photodiode is shown in figure 14.23a and a typical IV characteristics in 14.23b. Note that to create an EH pair, we spend some energy. Therefore, when an electron and hole recombine, the energy is released in the form of light, radiative recombination, or heat, non-radiative recombination. It depends on semiconductor and the method of fabrication of the p-n junction. For the fabrication of LEDs, semiconductors like GAAS and GAS, GAP are used in which radiative recombination dominates.